In this question we read that a spherical balloon is inflated so that its radius increases at a rate of 2 centimeters per second. Find the rate of change of its volume when the diameter is 30 centimeters, then when the surface area is 676 pi centimeters squared. Okay, so let's take a look. First of all, let's figure out what's going on here. First of all, we're talking about a spherical balloon. Okay, so once again, we're kind of looking at a scenario that looks like this, kind of looks like a circle here. Let's identify here, what do we know? Well, first of all, we know that the radius, actually maybe I should zoom in a little bit here. We know that the radius, okay, is increasing at 2 centimeters per second. Okay, actually that's probably a little bit too much there. Okay, and what we're looking for, what we want, whoops, I was about to write what we want is the rate of change of the volume here, dV by dt. I don't know, that's what I'm looking for here. But I've got two scenarios here. First of all, when the diameter is 30 centimeters, so the diameter is 30 centimeters, but bear in mind that when we're looking for the volume, okay, remember that the volume equation is going to be 4/3 pi r cubed. Okay, so I know that relationship already here, 4/3 pi r cubed. Okay, make sure that's clear there. This is in terms of the radius here, so when I say that the diameter is 30 centimeters, really what I'm saying here is that the radius is 15 centimeters. Okay? Now, I'll come back to this in just a second. In question B, okay, or part B, we know that the surface area here is at the given point that we're looking for, or that we're interested in. The surface area is 676 pi centimeters squared. Okay, so in question B, we know that the surface area is going to be 676 pi. Well, now, what's the formula for the surface area of a sphere? Let's figure out what this is trying to tell us. Well, the surface area is going to be 4 pi r squared. Okay, so at that exact instant, it should be clear that what we're trying to give you at this point is give you the radius. So in this first case here, question A, I gave you the diameter because I really wanted you to find the radius. Here, I'm giving you the surface area because I really want you to find the radius. So now we'll take that, the pi's will cancel here on both sides here, then we'll take that 676, we'll divide that by 4. We'll get 169 is equal to r squared. And then all we got to do is take the square root of that, and it should be pretty clear, I think, that it's 13. Now you might say, you could argue here that this is plus or minus 13, but we're talking about the radius of the sphere here, so it makes sense that this is going to be 13 centimeters, positive 13. So now, let's take a quick look over here and we'll start to answer the specific questions here. So first of all, for A, okay, now, we're looking for dV by dt. We're looking for the volume here. So the formula for the volume is 4/3 pi r cubed. Okay, I know how fast the radius changes, and I have a specific value for the radius, and I'm looking for how fast the volume changes. So I'm just going to take the derivative of this. And again, I know that this is what I want to do here because I've got a relationship here between the volume and the radius, and I already have some information about the rate of change of the radius, and I'm looking for the rate of change of the volume. So that's exactly what I want here. There's no extra variables here. This is perfect. So dV by dt, and remember I have to take the derivative here implicitly, okay, because there's no time mentioned here, and when we're talking about related rates, we're taking the derivative with respect to time. And so this will become 4/3 pi, and then the derivative of r cubed will be 3r squared. And dr by dt, we have to multiply by the derivative of the radius here. This is the chain rule, okay? We got r cubed here, bring down the 3, subtract, and then we multiply by the derivative of what's inside. Okay, so now, well, we can simplify that. I can see that the 3's will cancel here, and I've now taken the derivative, so now I can substitute in the value of the radius. Now for part A, we determined, okay, over here, we determined that the radius was equal to 15, so I can plug that in now. So this will be 15 squared. And I know that the dr by dt was equal to 2. Okay, so my volume here is going to be, the rate of change of my volume, I should say, is 4 pi times 15 squared times 2. So now I'm just going to multiply that together there, and I will get 1800 pi centimeters cubed per second. Yeah, because it was in terms of centimeters and seconds here. Now, we might want an exact value here, so we'll just multiply that by pi. I'll do this on my calculator here. And so this is approximate. This is exact. Okay, didn't require rounding here. But as soon as I got a round, this is an approximate answer. This is approximately 5,654.9 centimeters cubed per second. Okay, so there's the answer to part A. Now let's take a look at part B. And we've already done a fair bit of the work here, because really the difference between part A and part B was just how I gave you the information about the radius, the specific value of the radius. But everything else here is basically the same. We're still looking for the rate at which the volume changes, given the rate at which the radius changes. So we're still using this formula right here. The derivative, once again, with respect to time, 4/3 pi, this will become 3r squared dr by dt. And in this particular case here, okay, again the 3's will cancel, pi. In this case we know that the radius was equal to 13, and then dr by dt was going to equal, was equal to 2. And so now I'll just go to my calculator and evaluate this, and it turns out when you plug this all in, again leaving the pi in there to start off with, we get 1,352 pi centimeters cubed per second. And again, if we want this, okay, to the nearest tenth, we'll just plug that in, multiply by pi, so we'll get 4,247.4 centimeters cubed per second. Okay, so there you go.